then E in equals to E out, then Q minus W equals to U. So we assume the overall change in the system doesn't change. Now I'll make a bit of space here. Okay, so that's what he was asking just now. Now in general, when we solve this question, right, when you use Q minus W equals to delta E, we are assuming that we assume that we don't know what are the directions of the Q and the W first. So meaning when you solve this question, or when you solve it, then let's say your Q you get negative, then it is Q out. If you get positive, then it's Q in. There's also another way where, let's say you do know what are the directions of the energy. What you can do is this. Usually we can just write this up. Minus work out minus work in. That equals to delta E or delta U. So but when you do this, right, make sure that all the value that you submit is positive value, because you have given the direction to all the work in this case. So usually this is also one way that you can do. So let's say you know that the question, for example, you know that there's a Q in, then you just cancel Q out lah. There's no Q out. So then you see that you're expecting work out or you're expecting work in, then also you cancel off. So usually it will be one in, one out, one in, one out. You cannot have all the energy to be in or all the energy to be out. Okay, so two ways again. If you use Q minus W equals delta E, you are assuming that you do not know what is the direction of the final energy, in or out. If you use Q in minus Q out, work out minus work in, all the values are supposed to be positive because you already you have given the direction to all the work, all the energy. Okay, can you understand what I was trying to say? If not, then we look at example again later. Alright, so this is the general equation for closed system. Alright, now here is more or less the problem solving steps or energy analysis steps when we are dealing with this type of question. Now, of course, the very first thing is, you haven't learned this yet, but you would have to understand whether you are dealing with a closed system or open system first. Because open system and closed system would have different ways of solving the question. So of course you have to decide which one first. But here our examples will only be closed system because we are still studying closed system. So that will be the first method, the first thing that you need to do. Second, please observe or note what substance you are dealing with first. Whether you are dealing with liquid vapor or ideal gas. So again, in our cases, this will be water or R134A. So these are the two that you have. For ideal gas, mostly we deal with air. Now, for air, right, actually we do have a table as well. So actually there are two methods to this. We will do it when we come to this lah. But if you are dealing with H2O or R134A, we always usually properties from tables. There are no equations to calculate the properties, okay? I mean, not including those equations for like quality and stuff lah. We always use tables, so always remember this. H2O, R134A, do not use the ideal gas equation. We always use the table. Then for air, then we can use the ideal gas equation or the table. We have the method again. When we come to it, then you will know. So once you are done with this, right, then the rest are a bit ambiguous. So the properties and the processes, this is where you need to, again, it's also noting down. So note down what are properties given to you, how many processes are there, so how many states, how many processes. So usually one process you have two states. So what are the properties that the question gives you for initial, final state, something like that. And then this is not a must step if the question don't really ask you. Meaning if the question don't ask you to draw any graph or diagram, you don't have to. But usually I find it helpful to kind of illustrate it out so that you know what process takes place in this case. Okay, once you're done, then you apply the energy balance equation. So for closed system, you apply the equation that we saw just now. Q minus W equals to delta U plus K plus E. Okay, then after that, yeah, this one is just maths lah. You have to see what you have. So simplification and substitution. So simplification means that it's anything that we can ignore, anything that we can cancel off, and then what we can replace. Okay, so these are the things that we can do. Is maths basically. Alright, so these are the steps. The first three are the more important one because, yeah, once you manage to note down everything, most of the time you will be able to solve the question. Okay, we look at one example first. So this example, I believe, will also serve as a lecture actually, because there is one new information in this example, which is the first question. So let's read this out first. A piston cylinder device contains 25 grams of saturated water vapor that is maintained at a constant pressure of 300 kilopascal. So this diagram, let's say in exam, right, we won't put all the information on the diagram. You might get a diagram, but not everything will be written there, so you have to note everything down yourself. So that is also one thing that I find helpful when solving these kind of questions, because questions usually are very long. This is considered a short question. So you might lose track of what you have and what you are trying to solve. So most of the time for me, I start off by just writing down all the information given first, so that I know what I have. Okay, so here you have 25 grams saturated water vapor and constant pressure of 300 kilopascal. A resistance heater is turned on. So this constant pressure actually is entire thing. So a resistance heater is turned on and heat loss of 3.7 kilojoule occurs in this case. So number one, show that the boundary work WB and change of internal energy delta U can be combined into delta H. This is what I will show you. Then after that, you need to find the final temperature of the steam. So this one will be through the table. So here if you follow the step, you will see that this is closed system, and we are dealing with H2O here. So then you look at the information given. So everything is noted in the diagram as well. So mass is 25 grams. The whole entire pressure is with the entire process. The pressure is 300 kilopascal, and saturated vapor. Then you have a resistance heater. Okay, so we go to the next page. So you can see here that what you have here is electric work in, you have Q out, you have a boundary work. So usually it is very easy to miss boundary work, because boundary work you will not be told about the boundary work in the question itself. So you have to see whether there is an expansion or compression happening in the question. Okay, so this is also very closed system question. So this is the basic assumption. So like I said, for closed system, most of the time, the most basic assumption that you should have is delta K equals to negligible K and PE, the change at least. So we start off with this equation, as you mentioned. So here, again, you note down what are the energy involved here. So for the Q, we know that there is only Q out, right? So it will be negative Q out, then minus. So in this case, electric work is work in, so it's negative WE. Then boundary work is out. How do we know that? Actually, did the question say anything? Let me see. Okay, technically speaking, it doesn't say that this is an expansion process. So there are two ways. One is through logic. The other one is actually through you still have to check the volume lah. But anyway, in this case, most of the time question will be more clear. So in this case, the Q out actually is not a cooling process, it's just a heat loss. So your main process here is actually still the resistance heater process, right? So if you heat up the water, it expands, then it should go out. It should expand. So it should be a work out, a boundary work out. Okay, so one thing to take note as well, this was something that I mentioned before this as well. You will see that even though this is a resistance heater, so by logic you would think that we are supplying heat to the system, right? So, but then we write WE here instead of QE, because the work that is crossing the boundary is electric work. So we write electric work. Even though actually if you put it as Q in and then you use back the same value, actually you will still get the same answer. Just the meaning a bit different. Electric work, the electric power that is supplied to the the electric energy that's supplied to the resistance heater. Is the electric work, WE. So you have resistance heater here, right? So this WE is the power, the energy that you supply to this heater. So that is the one that is crossing the boundary. Okay, so far can you understand what I'm trying to do? Okay, just applying the equation. Then we submit everything that we know. Okay, so now boundary work, since this is a constant pressure process or isobaric process, we know that boundary work is the work under the PV diagram, right? I mean the area under the PV diagram as well. And also from the previous section, we derived that for an isobaric system, boundary work equation is P naught V2 minus V1. So we sub in the equation here. Okay, so from here, you move this entire thing to the right hand side. It becomes U2 plus P naught V2 minus U1 plus P naught V1. And when we group this together, from the pure substance chapter, we kind of talk about this, whereby we say that H equals to U plus PV. Now, in this, so then we group this together, it becomes H2 and H1. So ultimately, this equation will be left with basically delta H. So now, one thing to take note here is that, actually quite a few things, but okay, now, like in this question, you can actually find boundary work, right? So it actually doesn't matter whether you want to use delta U or you want to put it to the right hand side to become delta H. It is just an alternative for you because you can get delta H value from the table, you can get delta U value from the table. So this is one way to simplify the process, but not necessarily, you don't necessarily have to use this. But of course there are cases where this will be useful. Okay, like let's say you don't have enough example. So these cases, this case, right, you have to remember this. This case is only applicable to constant pressure process or isobaric process. Because if the pressure change, then this line won't be as nice anymore. It won't tally with the value from the table. So only for constant pressure process. Any other process, you cannot move the boundary work to the right hand side and then just change the internal energy to enthalpy. Okay, only for constant pressure process. Because then you, or else, right, you will be looking at them at different level, maybe the value. So it also, it doesn't matter whether we are dealing with a boundary work in or boundary work out. Regardless, the value will be the same. If you come across such question, like in tutorial or example, you can actually compare. You do both methods, you will see that you will get, it won't be exactly the same. There might be very slight difference, but not very significant difference. So you will see that the value is the same. So U plus PV equals to H. Okay, so this case is only applicable for constant pressure process. So in short, if let's say the question doesn't ask you to look for boundary work, right? You can just move it around, move it over, then you just use delta H to find the whatever that the question asks for. Alright. Okay, so now we try to solve the question. Actually, what does D ask for? So find final temperature of the steam. Right. So here we need to note what are the information that we have here. Right. So first off, we look for WE first. So WE, or the electric work energy to the resistance heater, will be VI delta T. So V 120, I 0.2 multiplied by 300 second. So again, this will give the answer in terms of joule. So we divide by 1000 to get kilojoule. So that is our electric work. So if, and then what is VI delta T? This is an electric energy equation. I think if you are from mechatronics, you shouldn't be asking me, to be honest. Have you learned this? Same thing. Power is work over time. Power is W over time. So W is VIT. Same thing. Okay? So this is actually P equals to VI. Yeah, better learn this. Okay, anyway. So this is electric. So here we get the electric work. Basically what we are trying to do here is we try to find all the information here to fit into this equation in order for us to find the final temperature. Okay, now maybe the method here is not so straightforward here. Now let's look at it here first. So for this question, right, let's say, actually what does, let me see what my method is. Okay, so let's say we use this method, negative Q out plus WE equals delta H. So we have this value, right, given by the question. We just found this method value, right? So here we have H2 minus H1. So for H1 we can find the information because we have two properties, meaning we know that it is 300 kilopascal. We know that it is saturated vapor. So you can find H1, right? So based on this you can find H2, but we cannot find H2 actually, because H2 we only know that it is 300 kilopascal. We don't have any other information. So this is what we are trying to do here. Okay, so for state 1, we know that it's 300 kilopascal, saturated vapor, H1. Okay, so you can get this from the table. Then sub everything into this equation, you will find that H2 is this value. So from here, we get the second information for state 2, which is H2. And now we know that P2 is 300 kilopascal. We can find from superheater table that T2 is 200 degrees Celsius. I will show you in the next slide. Alright, so now when you are solving all these processes and questions for closed system and open system, what we always try to do is to find the link between the two states or three states if you have three. So because most of the time, again, we need two independent properties in order for us to be able to read the table. So you always need to be able to find the link. So meaning what link between them. So like in this case, we can use this equation to find. So there's no fixed method here. It is more on practice lah. You will see more in the tutorial again. So here you can see that the link here will be we can use this equation to find H2. So H2 is our second property. So based on this, we go to the table. So we know that in state 2 we have 300 kilopascal. And state 2 is 300 kilopascal and H2 is 2864.9. So 0.3 megapascal. We can look for the H value column. You have to look one by one basically. So here we can see that there is one value that is 2865.9, which is on the same row as 200 degrees Celsius. So this value is not your exact value, right? So this is one thing that a bit hard in term, not to say hard, but a bit ambiguous in thermo. Usually when the value is close enough, of course you just write first, then you say that it is, then you can say that H2 is approximately, you use this symbol, 2865.9, then you can say that T2 is approximately 200 degrees Celsius. Because if you are to interpolate this question, right, this answer, right, so if you are to interpolate, you interpolate with this one, right, 2761.2. You will get like 199 point something. So it is not very worth it to do this kind of thing, so we just approximate it. So the issue here will be how close enough is close enough for you to approximate. I don't have an answer for this. So the questions usually I'm the one who design. So it usually means that if it seems that it is close enough, then it is close enough. Let's say if I want you to interpolate, the answer that you will get will not be 2864.9. It will be like 2800. Like it is obvious enough that it is in between the two, so that you need to interpolate. If you think that, if you look at it, you look like it's very close, then it means that you can approximate. There's no real answer to this, because sometimes it is very hard, because when you have multiple processes, you can't really get the exact value. You can't design it that way. Okay, so if I don't want you to interpolate, you will see that it looks very close. Then you can just approximate. Of course, you will not be wrong if you want to interpolate, but it's just a waste of time. Okay, so this one, yeah, you have to see that. So like in this case, it's considered close enough, because like I said, if you interpolate, you will get like 199 point something. So don't have to do it. Okay, clear? So this is how you get the final temperature for this particular question. Okay, so now the next question, I'll let you try. So here we have an unrestrained expansion of water. So a rigid tank is divided into two equal parts by a... Actually, this question kind of, the diagram kind of tells you what happens, so you can try based on that also. A rigid tank is divided into two equal parts by a partition. Initially, one side of the tank contains 5 kg of water at 200 kilopascal and 25 degrees Celsius. And the other side is evacuated. So it means that there's nothing over here. You only have one side at first. So the moment you remove the partition, water will try to fill in the blanks. So when you try to fill it, then it will change state. So, and then it is allowed to exchange heat with its surrounding until the temperature in the tank returns to the initial value of 25 degrees Celsius. So initial state, all the information are given here. Final state, you know that T2 is 25 degrees Celsius. If you look at the diagram, then you know there's a pressure here, the pressure value also lah. But here, technically speaking, this diagram shouldn't be there. So you wouldn't know. All you know is T2 is 25 degrees Celsius for now. Okay, so look at the question. So the question actually is also a guide on how to do the step-by-step guide. So determine volume of the tank, final pressure, and also heat transfer from the process. So you need to, so you find the volume of the tank first, then after that you look for the final pressure, heat transfer from, and then heat transfer from the process. Okay, try this out. So again, like what I said just now, you try to find the link between state 1 and state 2. What are their common thing in this case?
Return to initial value.